Hi, and welcome back to Blockchain Fundamentals with Bill Laboon. Today, we're going to go more into depth on how exactly hashing works, how digital signatures work, and finally, we'll use all of what we have discussed so far to make a real, live, functioning cryptocurrency. However, it will have a centralized ledger. We'll discuss more about how to make it more decentralized in the next lecture. So let's dive a little bit into how hashes actually work. Remember that hash functions compress some arbitrary length string into a fixed size output. And remember, we had some initial attempt at this called bad hash. What we did then was convert each character into a corresponding value and sum them up with the modulo the size of the expected output. There were a variety of problems with this, with bad hash. You can go back and look at the lecture on the original lecture on hashing to see all of the problems with it. However, there is a different kind of scheme called Merkle-Damgard transforms, and you probably recognize that name Merkle from Merkle trees, which provide a better way of generating hashes and doing it in a scalable way. So Merkle-Damgard transforms solve some of the problems of converting an arbitrary sized input to a fixed output using what I think is very interesting here, a very similar process to generating a blockchain. So for the input, what we're going to do is chunk the data into blocks of an equal size. So for example, every 8 characters or 512 characters or whatever n characters will be chunked into a block. If there is remaining space, so for example, assume we have 8 character blocks and we have 20 characters that we wish to put into a hash, then we will pad this final block with an additional 4 characters. And that way we can create 3 8-character blocks. What we're then going to do is run the same function on all of these blocks and use the output from the preceding block as input into the next block. So what we're going to do is have a compression algorithm which takes 2 arguments. The current block, which is of size m, which remember m is a constant. We made sure that our blocks are all of the same size, and the previous result of size n. So both of the inputs coming into our compression function are going to be of fixed size, a fixed number of bits. The output is also going to be a fixed size n. So is going to be, remember we accepted the previous result and passed into this new one. Just like imagine Legos being stacked. The holes from the bottom Lego, or the pegs in the bottom Lego fit exactly in the holes in the top, and we can continue adding onto these Legos. We can keep repeating this as many times as necessary. So if there's a single block, this hash function will work. If there are 100 blocks, the hash function will work. Because we're always accepting the input from the previous and pushing it into the next. So here I have a graphical illustration of this. So we can see here we have chunked up our data into 4 blocks. Block 1, 2, 3, and again, we could take this up to size n. It's arbitrary. However, the block size must remain fixed. In our example, I set it as 512 bytes. You will notice C is our compression function here, but for our initial block, we need to have an additional value being passed in. Just like with our blockchain, we had null values, so we needed to think of what is the hash of null. We're going to have something called an initialization vector. So for the initial call to this compression function with the block 1, since there is no preceding block, instead we're going to pass in this initialization vector. This is a constant defined for the hash algorithm. So whatever your hash algorithm is, it will have some specific initialization vector. So if we walk through this, we run the compression function on block 1 and the initialization vector to get an output, n. N is then passed in to the compression function again with block 2. The result of that, n prime, would get passed into block 3, etc., 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 until finally we have our final 256-bit output. So you can notice here we keep getting, from every time that we call the compression function, we're getting a 256-bit output. So we can see here it doesn't matter what the size of the input is. We're always going to get a 256-bit output because we're simply iterating or repeatedly running this compression function. So just as an example, with a very small input where we have 16 bits as our block size and 8 bits as our compression function output, we can see that the block AA98 is the first 16-bit chunk. So you see at our bottom, compress AA98B97608 ... So we're going to split this up into 16-bit chunks, which is equivalent to 4 hexadecimal characters. Our first block, AA98, gets passed in with our predefined initialization vector, 2a. This is run through the compression function C, and we get the result B7. That becomes part of the input for our next call to the compression function, which accepts the second block, B976, along with B7, giving us the output 3.2. Our next compression function gives us, you pass in 0876 as the third block and the output 3.2 to get 7.8. And here is where it's interesting. So our initial input, we could not separate that into 16-bit chunks. So we're going to add a second value here to fill in or pad, or what's sometimes called strengthen, that final block. So in this case, I put 38 there. What you're going to see in most hash functions is that this strengthening is going to pad it with zeros, but it's arbitrary as long as it's defined what data goes there. So here we have 1938 passed in with 78 to get our final result of C4. So we have 56 bits, but the output was an 8-bit hash. So now you see how hashes work behind the scenes. And again, I find it very interesting that this is very similar to how a blockchain works. You're just passing data that builds upon previous data. Now we're going to look a little bit more deeply into digital signatures, which are a very fundamental part of blockchain and cryptocurrency in general. So we've already discussed how we can use cryptographic hashes to hide information, but we can also use them to prove our identity. We very briefly discussed this when we discussed encryption when we talked about MACs. So we want a few characteristics for a good digital signature. So if I want to make a signature, only I should be able to make that signature. No one else should be able to copy it or make their own signature on a piece of data. But conversely, anyone should be able to tell that that signature did come from me. They can verify that it's valid. The signature can't be reused. It's tied to a specific document, and any document can be considered a set of bits. So unlike a real life signature where somebody could copy and paste to any document, your signature looks the same or very similar no matter which document you sign, we really want to make sure that somebody can't just copy your previous signature and use it for a different bit of data, since copying is extremely simple in the digital world. Note that this doesn't mean that signature creation has to be deterministic. We could have multiple signatures on a file that all do indicate that you own that file or that you have signed it. So note that digital signatures are actually much more powerful than a handwritten signature. Handwritten signatures can easily be forged. It's hard to validate. It's hard for me to say that this particular signature was written by the same person as another, and can easily be reused. So to create a digital signature scheme to meet all of these characteristics, we're going to need to define 3 algorithms. The first is generate keys. So given a key size, return a key pair. That is, a public key used for verification and a secret key used for signing. So recall back, this is basic public key cryptography that we discussed in our lecture on public key cryptography. We also need a sign function. So given a secret key, SK, and a message, return a signature for that message. And finally, a verify function. Given a public key, a message, and a signature, return a Boolean value, that is true or false, indicating whether or not that is a valid signature. So you'll notice to verify that somebody signed with a secret key, all you need is the public key. So let's play something called the Unforgeability Game. So here we have the good Bill who knows the secret key and the public key, and the evil Bill who only knows the public key. Now, if our cryptography is all that it's cracked up to be, this Unforgeability game should allow us to do the following. So evil Bill sends good Bill a message, M sub 0, and good Bill signs it. So he signs it with his secret key, gets the signature, and sends the signature for message M sub 0. Then evil Bill sends over message M sub 1, which is a different message. Good Bill once again signs this. He sends his secret key, he sends the signature that he after signing the message with his secret key. And he does this n times. Now, after this, if the attacker can send some different message, M prime, with a signature, and where M prime is not in M sub 0 to M sub n, that is an entirely different message than was sent before, if the others can verify that that message came from good Bill, again, the only one who knows good Bill's secret key, then the attacker wins. In this case, they have been able to successfully forge a message. The reason that they will get an essentially unlimited or arbitrary amount of attempts at getting a proper signature is because when we put data on the blockchain, it's going to be visible to everyone. This data, these signatures are going to be available to anyone. And so people are going to be able to get a wide variety of messages and see what their signatures are. So what we want to prove in this Unforgeability game is that even if you have a large number of these messages and see their signatures, unless you know the secret key, then you will not be able to imitate the person who originally signed these documents. So here is actually how we would like this to work. That the attacker loses. No matter how many times good Bill is going to ask evil Bill to sign messages, good Bill is never going to be able to generate some signature that is going to pass the verify pk m prime sig function. The attacker will lose. This is something that is in fact possible to do, at least on a day-to-day basis, with modern cryptography. Now, obviously, because there are only a limited number of possible bits, there's there's a fixed size, it's not arbitrary, and so given enough time, the attacker could run every single possible iteration and possibility to see that they would get a valid signature. However, what we're going to see is that very quickly, as we increase the number of bits in our hashes, this becomes infeasible. That you would have to wait for millions or billions or trillions of years before you would even have a chance at getting a correct result. And so even though theoretically there are possibilities to break this cryptography, on a day-to-day basis, it is so unlikely that we can consider it as messages, once it's been signed, as basically unforgeable. So if we have a way of unforgeably proving who we are, we have a sort of digital identity. So I can always say that this is me, because if I'm the only one who knows the secret key, I'm the only one who should be able to sign messages. If I want a new identity, I can always make a new key pair. I can just become another face in the crowd. So this is interesting, where it's very easy to prove that someone or some message is from you. It's very difficult to prove that it was not sent by you. So, if someone does want to impersonate me, though, it's going to be computationally infeasible. So now that we know that we can publish our public key and keep our secret key and then have an identity, we actually can start generating, along with some of the previous data on data structures to use, we can actually start generating an actual cryptocurrency. So the first one I want to discuss is from the book Bitcoin and Cryptocurrency Technologies, which is a very in-depth book, and I recommend you read it if you'd like to understand really in-depth how Bitcoin works. So this is a cryptocurrency called Goofy Coin. And Goofy Coin has a few simple rules, but it's going to allow us to create a valid and functioning cryptocurrency. So the first rule is only one entity is allowed to generate new coins, and that's Goofy. Every time a new coin is generated, it is going to belong to Goofy. The second rule of Goofy Coin is whoever owns a coin can transfer the coin to somebody else. So this is what we want. Goofy will be able to generate coins, and Goofy can then send those coins to others. Those people can then send them to others on their way. So how do we generate these coins? First, Goofy generates a unique coin ID we'll call U. Then Goofy computes a digital signature S with his secret key. So we now have an ID and a digital signature of U proving that Goofy is the one who generated it. So we now can take U and concatenate it with S, that is, combine it with S, and we now have a coin. Anyone can verify that this coin is valid using Goofy's publicly known public key. So they can run, remember, one of our primitive cryptographic operations, verify, with U and the signature to determine if a coin has actually been generated by Goofy. Now let's make some transactions. And remember, we already talked about how transactions can be stored in a blockchain. So in this transaction, Goofy has a transaction, give this to Alice, where this is a hash pointer to a coin, and Alice is just Alice's public key. Then Goofy signs the transaction with his private key. So now there is a signature, which can then be put on the blockchain, and anyone can verify that Goofy generated the coin, one, so it's valid since Goofy generated it and he is allowed to generate coins, and that there was a transfer to Alice, or at least Alice's public key. Since Alice's public key is specified in the transaction, if Alice tries to send the coin to someone else, she'll need the secret key corresponding to that public key. In other words, anyone can send Alice money, but only she can send it to someone else from there. You need the public key to send to, you need the secret key to send from. And anyone can verify that the secret key that she used to sign off on sending the coin matches the public key that was used to give the coin to her. So now we have a little ecosystem here. Goofy can generate as many coins as he likes as long as he comes up with unique new strings. Whoever owns a coin can transfer it by saying, give this to the person with the public key X. And anyone can verify that the coins are valid by following the chain of ownership all the way back to Goofy. So here, Goofy, and remember that Goofy knows both his public key and secret key, says, I'm creating coin A763BA. The signature for that coin is 98. And recall, only Goofy knows how to generate that signature. Alice, knowing only the public key of Goofy, can run the verify function. So she can tell coin A763BA, signature 98, was in fact signed by Goofy. Thus, Goofy has made the coin and it is valid. Goofy would now like to send a coin to Alice. So Goofy knows the public key and his own secret key, as well as the public key of Alice, since the public key is publicly accessible and can be broadcast. Anyone's allowed to know the public key. It will give you no additional information on the secret key. So Goofy wants to give coin A763BA to the public key sub Alice. So Goofy signs a message with his secret key, and that message includes the public key of Alice. Alice knows the public key of Goofy, so she can tell that Goofy did in fact give her a coin. Why? Because she can verify that this message says this is going to Alice's public key and it was signed by Goofy. So Alice can then give Goofy whatever you would get in return for a Goofy coin. Anyone else can also look at this and determine that it's valid. So now Alice would like to give her Goofy coin to someone else. So she was going to give it to Bob. She creates a transaction saying that she is giving coin A763BA to the public key of Bob. So she signs it with her secret key, and the message includes the public key of Bob. So Bob can now verify not just the the previous transaction, the transaction sending it from Alice to Bob, but also the transaction sending it from Goofy to Alice, since all of this is going to be publicly available information. So Bob looks to see, was this coin that Alice gave me valid? Well, it was, looking backwards, it was sent to public key Bob, that's me. Here's my public key, and it was signed correctly. Before that, it came from Goofy to Alice, and it was signed correctly. And just follow the chain of ownership up, an arbitrary number of hops until we get back to the initial Goofy generation of the coin. So now I can verify, Bob can verify, Goofy gave this to Alice, Alice gave it to me. Because at every step, we can tell that before someone sent it, the message, the transaction, was signed with the secret key of the actual owner. That actual owner is whoever public key is specified and where that coin was sent to. So this allows us to create to verify that coins are valid, but there is a problem here. What if Alice gives a coin to Bob, but neither Bob nor Alice have yet told anyone else? Alice can do the exact same calculations to give the coin to Carol, and Bob would be none the wiser. So now Carol has the coin and Bob doesn't. Or maybe perhaps you could think of it as Bob having the coin and Carol doesn't. So here, this is called a double spend attack. So why? Because let's think about how this would work. So Alice, who's already given the coin away to Bob, but Bob hasn't told anyone yet. It hasn't been published. So Alice goes to Carol and says, hey, I'll give you a Goofy coin for some ice cream. So Alice generates a signature, makes a transaction, shows it to Carol. Carol, looking back at the information that's publicly available, says Goofy generated this coin and it was valid. Goofy sent it to Alice, that was valid. Alice sent it to me, that was valid. I can verify Goofy gave the coin to Alice, Alice gave it to me. There's no way of knowing, according to what we've done so far, that she's already given it to someone else. Right? So this is a pretty major problem. So let's try to fix this by generating Scrooge coin from Goofy coin. So transactions occur in Scrooge coin just like they do in Goofy coin, but there's an additional wrinkle to this. Scrooge is also going to create an append-only ledger where people verify that a coin transfer is official and has actually occurred. Scrooge can now determine that a transaction is valid. that is, that it was signed correctly, and also that there was never a double spend, that the same person didn't try to send a coin to person A and person B. Scrooge will sign the block. He will use his secret key to create a signature associated with that block. Right? And any transaction that's not yet on Scrooge's blockchain, his ledger, and signed with Scrooge's digital signature is not considered official. So if you're trying to transfer or buy something with your Scrooge coin, you can do the transaction and then wait to see it appear on the Scrooge coin ledger before considering it valid. So here we've got our nice Scrooge coin blockchain. Scrooge is going to sign the root hash. He's going to sign every block as one comes on. In this case, just for simplicity, I'm only showing one transaction per block, but you can imagine multiple transactions in a block. So here, since we get all of the assurances that we normally do with the blockchain, that there hasn't been any tampering, and we have one centralized place where the transactions are stored, we don't have to worry about double spending or people modifying the ledger under our noses. So now when Alice tries to double spend, note she's already given the coin A763BA to Bob's public key rather. She then tries to give the coin to Carol, but Carol can look through and see that one, yes, the coin is valid, it was sent. However, she checks Scrooge's blockchain and Alice no longer has possession of this coin. She's already sent it to Bob. So here, by having a centralized ledger, we can avoid the double spend attack. So this is great. We now have a cryptographically secured currency, and we have a way of avoiding double spend attacks. But we now have a centralization vector. Scrooge coin works if we trust Scrooge. So Scrooge can never steal coins. He doesn't know the secret keys of the individual account holders. And since he doesn't know that, he can never take a coin from one person's account and send it to another. But by having this centralized ledger, there are a lot of vulnerabilities that we have just introduced into the system. Scrooge can blacklist users. That is, he can say any coins that go to this public key, I am no longer going to write down any transactions that they do. Or even a specific coin. If Scrooge thinks that a particular coin isn't valid, then or doesn't like it, or he can say that this coin, I'm not going to include any transactions including this coin ever again. Scrooge can generate new coins for himself. And there's, just as Goofy did, and there's no limit on the number that he can produce. Excuse me. Scrooge can stop updating the blockchain. He could say, I've gotten bored of this. Or he'll say, if you don't give me $1,000, I'm just going to stop using this and all of your Scrooge coins will be worthless. So he can hold the entire system hostage. So we can see there are a lot of problems with having a centralized blockchain. By having Scrooge be the one in charge of all of this. We are giving a lot of trust and a lot of power in Scrooge's hands. So far, the technical challenges that we have already looked through and solved to get to this point have been, I hate to say minimal, but basically minimal. This is where earlier cryptocurrencies up till the mid-2000s had really got to. All of them relied on some sort of centralized intermediary to help avoid the double spend attack. The key technical breakthrough of Bitcoin that allowed it to become a functioning cryptocurrency and really was the breakthrough that allowed things to be decentralized was coming to a consensus of valid transactions without any sort of coordinating entity. So in order to do that, what Bitcoin had to do was come up with a way for users to agree on a single, authoritative, canonical blockchain without having a particular person or entity in charge of it. Users needed to agree what transactions are valid, which actually occurred and which did not. a way to get IDs assigned in a decentralized way, and a way for coins to be generated in a decentralized way. How do we get coins in a fair way to users of the system? In the next lecture, we'll talk about how to take this centralized cryptocurrency that we have already discussed and turn it into a decentralized cryptocurrency that anyone can take part in and that nobody can control.